Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today as it is every day here in my virtual classroom. Stepping outside, enjoy some Thursday night. Don't enjoy this. I started this video because this game. I think Christian McCaffrey just got hurt, and Deshaun Watson doing Deshaun Watson things and not being active for the Texans means this is probably the most boring Thursday night football game. Actually, I don't know. We'll see. There are a lot of boring Thursday night football games, but this is definitely among one of the ones that I'll just let play in the background, and whatever happens, happens. Hey, guys, today we are going to be working with polynomial functions and graphing them out of what's called factored form. Actually, I think out of the book they call it intercept form. Just getting their basic behavior. You know, this time it's not going to be about specific points all around. We're going to get intercepts. We're going to get end behavior on these things, and, you know, going from there, it's just a matter of, you know, what does it generally look like? What does it generally look like and the features that we can have from that? Its characteristics are the most important part for us, and how can we come up with the graphs based on equations? How can we come up with the equations based on the graphs? And not necessarily get every point, but just enough critical points to kind of make sense of things. I got enough practice problems here that I don't actually know how this will go when it comes to time based stuff. So you know what? Whatever happens, happens here, guys, and I'll just let this thing play out. So here we go. We're going to go ahead and get started here, and we're going to be looking at and by the way, so the first several questions are talking about using a graphing calculator to do something. Now, I'll let you know right now, homie, I am a graphing calculator right here. You see, no, I'm going to go to a graphing calculator to show you the basic understanding of what the difference is between odd and even degree functions, and how odd degree functions behave like odd degree functions all the time, and even degree like even degree all the time. And then we'll just get our own little drawing out from it. I'm not going to use a graphing calculator for them. I'll just show you what they look like so we can keep using them for the future problems. So that way I don't have to type them out and work it, and I don't know what kind of graphing calculator you'll have to work with. So it's totally fine for me. So it says use a graphing calculator to graph the polynomial function, then use the graph to determine the function's domain, range, and end behavior. Use what's called interval notation for, interval notation for domain and range. So I did prep, not these functions specifically, but I prepped functions of any sort of degree right here. Oh, let's see, let me get it up. 1 second. Right here. And what you're going to see here on the side frame, some get cut off by my head, and that's okay, I'll state what they are, but you see even degree functions right here. X squared, x to the fourth, x to the sixth, x to the eighth, x to the 10th. Degree meaning the exponent in the term in and of itself. And what happens here when you graph these? You guys should know an x squared is a parabola right here. X squared is a parabola, and you know that's what it looks like, that's what it does. But did you know that x to the fourth is also, and honestly, I don't even know if it's actually called a parabola anymore, but x to the fourth is also parabolic in nature. It will have this idea that it will go from decreasing to increasing and have a vertex of sorts, but it will have a little more sharper angles to it. And of course, it goes higher over time. Here's x to the fourth in blue. It'll go higher over time, of course, at lesser x values, but between 0 and 1, it actually squares off a little bit more, has a bit of an angle, because when you multiply numbers less than 1 by themselves, like 1/2 times 1/2 times 1/2, etc., the numbers become smaller. So you get smaller y values less than 1, and then when you pass 1, it goes greater. So when you get x to the 6th, let's compare x to the 4th with x to the 6th. You can see x to the 5th gets just a little sharper. Let me keep x squared up there. And then x to the 8th here is in purple, and you can see there's little diminishing returns there. It's getting a little less cornered over time, but it's getting more cornered. When you get to x to the 10th in black here, compare x squared to x to the 10th power. Notice how it really starts to angle off, but it gets really steep after that. Regardless, as I zoom in right here in black, you know, they hit that vertex of 0, but you can really see how it angles on those. Basically, though, the basic idea is it's parabolic in nature. These are all even degree functions because when we raise to an even power, the result is positive if you're plugging in a negative value, and it's positive if you're plugging in a positive value. Now, if you flip something over, like negative x squared, something like this, it is going to flip over, and that's something that you have to know. It reflects across the x-axis, and that's something we're going to pay attention to when we do our numbers there. Now, odd degree functions won't have that characteristic. Let's just start with x to the first power, which is a little more basic than the other ones that you'll see. Here's x to the first power. Of course, it's linear, but it doesn't bounce back in any sort of way like that. It is odd degreed, which means when we plug in a negative number, you'll get a negative y value as a result there. But when we do a cubic function right here, and most of them are going to behave like the cubic, so I'm actually going to get rid of this right now. When we get a cubic, and we've done cubics already, you're now going to get this little thing right here. It's like a quadratic in its own nature, only instead of going up, it goes down, because once again, when you cube a negative number, your result is negative. And you'll see the same things in the 5th degree, 7th degree, etc., like you saw with the parabolas, that when it's between 0 and 1, like this, you'll get a little more of an accentuated angle, and when it passes 1, it goes sharper and higher. Here's 7th power, even though you can't see me checking that off, and here's the 9th power, like that, in a little more accentuated angle. So when you compare a cubic to a 9th power, you can see, again, more accentuated, but it has a center point. Instead of a vertex, it has a center point. But they all have that cubic-like nature, that curving through. Now, these are important to note, that the quadratic nature of something has like a bit of a bounce back, if you will, that vertex bounce back, and a cubic nature has a curve through behavior. You're going to have to know these for something later, but this is all important to note, that all the odd degree ones will have this kind of form. Okay, now that I've stated all that, guys, that's the only graphing calculator stuff I'm going to do. The rest is between you and I here. Let's go ahead and let's graph x to the 7th power. And, you know, there is no translation on here. It does go through the origin at its vertex, if you will. Maybe a little more accentuated in x to the 7th. I'm sorry, not x to the... maybe I do need a graphing calculator. More accentuated and angled than that of a cubic function, but whatever. It's going to look like that, right? It's a positive 1x to the 7th. There it is. And here we go. They're going to ask for the domain, range, and end behavior. Now, I'm not going to get deep into these. I'm going to state what they are and state why they are, and that's it. There's no bigger teaching beyond that. It's expected that you know domain, range, and end behavior based on what you've done in previous years of learning this stuff. But the domain, interval notation, by the way. The domain says how far left and right does this graph go. It goes as far left as forever and as far right as forever. It goes from negative infinity to positive infinity. These parentheses are not stating this as an ordered pair. They're saying it never touches negative infinity and it never touches positive infinity because they never could. They're not numbers. We would use square brackets if it did include values, and we're not including the infinities. The range, how low does it go? How high does it go? It goes down forever. It goes up forever. This goes from negative infinity to positive infinity. All real numbers there. End behavior states when we go forever right on x, when we go forever right, where do we find our y values? We find them forever upward. And when we go forever left on x, where do we find our y values? Forever downward. As in, they go that way for the rest of time. They don't change back and do anything beyond that in long term as we go toward positive and negative infinity. So the way we're going to write it is, as x approaches positive infinity, y approaches positive infinity. What I just stated right here was, as we go forever toward positive infinity on x, your points will be found up toward positive infinity on y. Approaches, not equals. We can't actually equal these values. And as x approaches negative infinity, as we go forever left, y approaches negative infinity, goes down. This isn't true of all of our graphs. This is true of the one that you see after you've drawn the graph of it. And that's the information that they wanted us to find. So number 2, let's go to number 2. We have another odd degree function right here. And on number 2 there, it's negative x to the 9th. Now, unlike x to the 7th, this one's going to be just a tick sharper. Not that I really have to draw that too much. But the negative means it reflects over the x-axis. So instead of going this way, we're going to be going this way. So negative x to the 9th, like this. And, you know, like I said, pretty accentuated as it hits through there and goes back down. Just, you know, do what you can. They care more about the fact that you do this with your graph, right? That's what matters. Domain and range, one more time. Does it go left and right forever? You betcha. Just because it goes super sharp up and down doesn't mean it's not still going left and right forever. I can plug in a billion into x. No, literally, I can. I'm not exaggerating. I can plug in a billion into x and I will get a value for y, so it's a part of my domain. I go from negative to positive infinity on x, not including the negative positive infinity. This is what interval notation looks like. And then the range is how far up and down does it go? Very sharply, forever. It goes forever up and goes forever down. So negative and positive infinity. You always do the lower bound first and then the upper bound second. Pardon me for not really drawing sideways 8s properly. And then, let me do a different color for these ones here. And then domain and range. Oh my goodness, what did I just do? And then domain and range, end behavior for this thing. We want to state as x goes forever left, where do we find our y values? As x goes forever right, where do we find our y values? So when I go forever right here, we're going to find our y values going forever downward. That's what they'll approach. As x approaches positive infinity. This time y approaches negative infinity. Let's get that correct. There we go. And as we go forever left, we go forever up. So as x approaches negative infinity, y approaches positive infinity. I don't know what's happening with my sideways 8s today. Something weird's happening. Yeah, 7-0. Look at that. All right, so those are two odd degree functions, one positive, one negative, and how we can mention those. Let's look at number 3. Number 3, f of x equals x to the 10th power. Remember how sharp that thing got, even sharper than x to the 9th. And this time, because it's an even degree, it will have that parabolic nature. It will bounce back. It'll have a vertex. So it's going to go in like this, hit hard at an angle like that. I don't know. Again, I don't know how important that is for us to necessarily get that. What's important is you draw essentially a parabola, a U shape. So, but positive x to the 10th, it does face upward. Now we have to answer the domain range questions in end behavior. Domain for this one here, it does once again go forever left and forever right. These don't actually, despite what it almost looks like, these don't truly go vertical. Otherwise, those wouldn't be functions. It still goes forever left and up, forever right and up. So it's going toward negative infinity to positive infinity. Now, this is a different range this time, guys. It may go forever up, but it does not go forever down. In fact, the lowest point it hits is when x equals 0, y equals 0. The lowest y value here is 0. When it asks how low does it go, there's actually a value. It goes as low as 0 on y. So I'm going to put a 0 here. And it goes up toward positive infinity on y right there. Now, we don't include the infinity because we can't reach infinity, but we do reach 0. So I will not put a parenthesis here. I will actually put a square bracket. For interval notation, this is the equivalent of saying y is greater than or equal to 0. That's what the square bracket gives you. The also equal to 0. It actually hits it. So there's the range for that. End behavior, when we go forever right, we go forever up. And when we go forever left, we go forever up. So you can tell here, right and up. As x approaches positive infinity, y approaches positive infinity. And as x approaches negative infinity, y also approaches positive infinity. It goes naturally up in both directions here as we go forever left and right. There's the end behavior. And lastly, number 4, we have f of x equals negative x to the 8th power. Now, when we substitute, we showed you with the negative x squared. When we substitute a negative value into x, we raise it to the 8th power, it becomes positive, and take the negative, it becomes negative. All our values here are going to seemingly just hit negatives, except for at the vertex here. So a little less sharp than the last one we just saw here. Let's get a different color, a little purple. A little less sharp than the last one you just saw, but still very, very gosh darn sharp here. Oh my gosh, what is this? That looks way too vertical for me. Let me just do it like this. Here we go. Oh, much better. Oh my gosh, that is so much better looking of a graph, even if it's maybe not sharp enough. But it goes upside down, right? The negative means it's going to reflect across the x-axis, and there we go. Okay, now domain and range. Once again, guys, domain all real numbers. You'll see, you know, we're gonna get some non-all real numbers someday, but you know what? Polynomial functions, all real numbers, all real number domains. Range, on the other hand, it goes down forever. So our lower bound is negative infinity, and it goes as high up as what? It hits as high up as 0 on y. So 0 is now the absolute maximum of this thing with no absolute minimum, and we include 0. So it goes like that. End behavior says as x approaches positive infinity and as x approaches negative infinity, this time you can tell, guys, that it's going to be going down forever. So this time y is going to approach negative infinity from both ends. So there it is. So, I didn't do huge teaching on the end behavior things in domain and range. I wanted to give you the basic understanding, even without a graphing calculator here, of what these will look like so we can do them here on out. And that's how we're going to answer those there in 1 through 4. Okay, moving forward. Using graphing calculator, and again, this time I'm not going to show you what these look like on a graphing calculator. I'll explain it as best as I possibly can for you and make sense of it. And the graphing calculator would do the same thing. You would just draw based off that. But after this, you're going to have to know what to do. So let's just go with me here. Graph the function using Mr. Robinson, and then use the graph to determine the number of turning points and the number and type of any maximum or minimum values you can have in the number and type of maxes or mins. You can either have what are called global maxes or mins and local maxes or mins. And what we do with that, the number of the number of global? Okay, well, anyway, we'll talk about it. So, okay, here's what's going to happen. Our basic nature of this graph is going to be based on the following concepts here. Number one, understanding that this is what's called factored form, or what I believe they call here intercept form. Now, I'm not going to fully multiply this thing out, but what you need to understand is if I did fully multiply this out, the leading term of this would be a cubic. I know this because I'm multiplying x with an x here. It doesn't matter if it's x plus 1. The fact is the leading thing is x. I'm multiplying x with an x to get x squared, and with another x here to get x cubed. I said I wouldn't multiply it out. I'll go ahead and multiply this one out for you. This would be x cubed plus 4x squared plus 3x. I just know that because I know how this mentally works. This is a cubic function. Now, we know with cubic functions, the following things happen. We know it kind of has this appearance, but there's a little more to it that we're going to do than just this. But the end behavior is as x approaches positive infinity, y approaches positive infinity. As x approaches negative infinity, y approaches negative infinity. We saw as much with any odd degree functions here. All odd degree functions will do that. But there's more that might happen in between. Maybe not end behavior, but the middle behavior, there's more that can happen. But the bottom line is I do know it's a cubic, but more importantly, I know that it is an odd degree function. So there's that. We're going to talk about that part on top of what we need to do with our intercepts. I don't really need this anymore. The next part that we need to talk about are these actual intercepts. What are intercepts? Well, this means y, right? F of x means y. This is y equals. What we're going to do, guys, is we're going to graph the intercepts, the x-intercepts of this function here. And x-intercepts are values of x when y equals 0. Now, I'm not going to do this for each problem, but I'm going to show you the basic nature of what if I set this equal to 0. Then we would use what's called the zero product property on these things, where it says if multiple things multiply together to make 0, any one of these could potentially be 0. Either x could be 0, or x plus 1 could be 0, or x plus 3 could be 0. If any of these are 0 at any one time, when you multiply it by it, the result is 0. One of these have to be 0. And you got to determine what the result is, if any more. If this x is 0, well, that's one of your values of x when y is 0. This is one of your x-intercepts, 0 for x. If x plus 1 is 0, subtract 1 from both sides, you get x equals negative 1. Basically taking the opposite of what's inside there. Unless they do something tricky with factored form, it's what value of x makes this 0? Well, it's the opposite of 1. It's negative 1. And same with this, subtract 3 from both sides, you get x equals negative 3. So your 3 x-intercepts, this is the part that I'm gonna rewrite. Your 3 x-intercepts are 0, negative 1, and negative 3. These are the points where we cross the x-axis on this particular graph. And don't take my word for it. Check on your own graphing calculator. But I'm just going to go ahead and tell you these are the 3 points where they cross the x-axis. So I'm going to rewrite them when I erase all this. This is how you'll generally see me do the work. Our x-intercepts we get will be x equals 0. Let's see, x int. We'll get x equals 0, x equals negative 1, and x equals negative 3. So as a graph, and this is going to be a really wide looking graph in comparison. As a graph here, we're going to be getting, here's negative 1, negative 2, negative 3, and of course there's 0 right there. So I know this graph crosses right here, and right here. I do know the graph hits those 3 points, my graph, whatever it is. Now, I mentioned this is a cubic graph. This graph is an odd degree cubic graph, which means its end behavior is going opposite directions. I don't know if you can see my arms. Let's see if I can see my own arms here. Which means we're going opposite directions here. End behavior is starting from the bottom on the left side and ending on the top on the right side. I know because it's a positive cubic. So how do we hit these points on this graph in a cubic? How do we hit these points in this graph in a cubic? Hitting these 3 points starting from down here and ending up here. Well, it's simple. The graph goes through this point right here. It's got to come back down and hit this point right here. And then it's going to come back up and hit this point right here. And it's going to finish off like that. And that's what this graph does by nature. Obviously, there's only so much room where I can fit all this. So this is how I'm putting it. This is how I'm putting it. But this is what this graph basically does. Now, what are the y values here and here? I couldn't tell you off the top of my head. I can tell you that your graphing calculator could tell you, and I could tell you that you can learn that through calculus, but they're not asking for those. They are asking for how many turning points there are, though. Number of turning points, there are 2. There's a turning point here and a turning point here. So I'm going to put it as TP. The TP is 2. There are 2 turning points on this graph right there and there. Now, the number of and type of maximum and minimum values, there are things called global maximums and minimums, and then local maximums and minimums. You also will sometimes hear them as absolute maxes and mins and relative maxes and mins. So if I ever say those, I apologize. That's what I mean. As far as global maxes and mins, global means globally around the world, absolutely what's the largest on this graph, what's the highest that this graph ever goes, and what's the lowest that this graph ever goes. Kind of like range, right? When we talk about range, it goes from, like, for instance, on these odds, it goes from negative to positive infinity. It goes as low as negative infinity, as high as positive infinity. And I say that understanding that it never actually hits negative or positive infinity. This graph goes down forever. This graph goes up forever. There is no absolute or global maximum or minimum on this graph here. You can't say negative infinity, positive infinity. Those aren't values. It never reaches those. And once you say it reaches that, guess what? It goes lower than that. There is no global max or min, meaning it never hits a low or high point because it keeps going up and down forever. Local maxes and mins are the points where they change direction. It's not about how low or high it goes. It's when your graph changes on a continuous function from increasing to decreasing. That's a relative or local max. And from decreasing to increasing, that's a relative or local min. So how many local maxes are there? How many local mins are there? This is a local maximum. This is known as a local maximum because this is where the graph goes from increasing to decreasing right there. Relative to the points around it, and doesn't matter how close you're saying, just relative to the points around it, it's the highest point in that set. That's a local max. This is a decreasing to increase here. This is a local min. So this graph features one local max and one local min. The turning points are your local maxes and mins, your local extremes of your graph there. No absolute or global maxes and mins. One local or relative max, one local or relative min. And I think that answers everything we're going to do. Use the graph to determine. Okay, that's it. I say that's it. That sounded like a lot, but now that we have that understanding, it'll make the other ones faster. Sort of. Let's look at number 6. Number 6 has the following. We have x plus 1 squared times x minus 1 times x minus 2. Ignoring the plus 1, minus 1, and minus 2 for a moment, I want to make mention, of course, once again, of what kind of graph this actually is. There's an x squared times x times x. That leaves you with an x to the 4th. At best, you know that the leading term is a quartic function, x to the 4th there. And we know that x to the 4th is an even degree, such as x to the 10th and x to the 8th, or negative x to the 8th. Even degree has a start up, end up, or start down, end down philosophy to it. That's what even degree functions do. So this x to the 4th will also do that. If it starts from the top, it's going to end at the top. And guess what? This is a positive x to the 4th. So this will have a start up, end up mindset. Now, granted, there might be some things in between where the graph turns. We're going to possibly see some turning point things here because of the nature of hitting your different x-intercepts. And that's what we need to find next. If you recall last time when I used that zero product property to say, if this times this times this equals 0, then either this equals 0, this equals 0, that equals 0. We're going to do the same thing here. Either x plus 1 equals 0, or x minus 1 equals 0, or x minus 2 equals 0. If x plus 1 equals 0, then x equals negative 1, right? You subtract 1 from both sides. You take the opposite. This is an x-intercept. I'm going to talk about this one a little bit more, though, in a second. When x minus 1 equals 0, you add 1 to both sides. You get x equals 1. That's another x-intercept. And then this one here says x equals 2. So if we get a basic nature of this graph here, guys, I'm going to draw something like this. And then let's go ahead and let's get some points right there. I'm going to get negative 1 on x, 1 on x, and 2 on x. And we hit these points here, here, and here. Now, it's important to mention that this is x to the 4th one more time because x to the 4th, an even degree function, has a start up, end up mentality. Now, if you look at this graph here, you might think, well, what you did last time was you if I start from the top, right, because this needs to start up, end up. If it starts from the top, like this one started from the bottom, ended up, I need to just cross through these points, right? So you might do something like this, and don't draw it just yet. You might say something like this. I'm going to go down here, and then I'm going to go up here, and then I'm going to go down here, and wait, it doesn't go down low forever. Okay, and I'm just going to go up there, and I'm done. You don't want to do that because we just hit some X-intercept that we never came up with. So, okay, well, that was kind of weird. Why? So how does it only have 3 X-intercepts, start from the top, and somehow end up at the top there without hitting a 4th X-intercept? What's going on there? What's happening? Well, what's happening, guys, is there is this one that's squared right here. This x plus 1 quantity squared technically means this is an x plus 1 times x plus 1 if you think about it that way. And there's x minus 1, x minus 2. If you really expand it, this is the true nature of it. This is actually what it looks like. So it's kind of like x equals negative 1 twice. We don't really write that. We don't have to draw this twice. But what we do have to understand is that this 0 behaves differently from the other zeros. It behaves in such a way that it will kind of have this quadratic behavior from it. Because x equals negative 1 twice, what we say is this thing has what's called a multiplicity of 2. That because that degree of 2 occurs for this factor of this polynomial here, this squared thing of this thing means this will behave like a quadratic at this point. And what I mean by behave like a quadratic is it's going to have a parabolic vertex-like nature at it. It's going to bounce off of the point. Instead of going through it, it's going to bounce off of it. So remember how I said it starts from the top? It does start from the top. But you know what? It doesn't go through this point. Instead, it bounces off of it like this. And then it goes back up, hits a turning point, and goes through. And I don't know where it's hitting this turning point specifically, but it's a turning point, goes down there, and then it's got to go up and through there. And at this point, you can now see it has that quartic-like behavior of start up, end up. It gets the turning points and only hits those x-intercepts right there because this one has what's called a multiplicity of 2 at x equals negative 1. It'll behave like a quadratic does in that vertex-like nature. Touch it tangentially at a single point like that instead of going through it. And I know that's a lot to take in, but the more that we do these, the faster this will go. I promise you, this will go faster once we mention these things here. So let's go ahead and let's answer the rest of the things from that. How many turning points are there? There are 1, 2, 3 turning points. TP equals 3 turning points. Those are local maxes and mins of this graph here. The types here. What is the absolute max? Oh, do we need? Oh, no, we don't need the absolute max and min. But are there any absolute maxes or mins? I was going to say if they need the actual number, I would need a graphing calculator for it. But they're going to ask if there are any absolute maxes or mins. Let's start with the absolute max, or global. It goes as high as forever. There is no global maximum. It goes up forever. We established that from number 5. Global minimum, though. There is a global minimum. There's a global or absolute minimum. It hits a low point. I can't tell you exactly what this y value of this low point is. It actually might be super sharp and low. I can't tell you. But I can tell you there is one. It exists somewhere between x equals 1 and x equals 2. Because this one bounces off at y equals 0. There's a negative y value right here that it does hit. It says how many are there? There is an absolute minimum. Or global. I see, again, they use the word global. I'm going to try and use the word global. But just understanding, you're going to use both terms when you hit pre-calc and calculus and everything else. There's a global minimum. There can only be one. I guess it can occur more than once, but there's only one time the global. Either there is or there isn't. There is no global max. How many local or relative maxes are there? How many local relative mins are there? Well, there is an increasing to decreasing point right here. That is otherwise known as a local max. And then there are 2 local minimums. One right here where it has that bounce back with a multiplicity of 2. There's a local min there. And then there's a local min here. So there are 2 local mins. One of the local mins is also an absolute min or a global min. And then there is 1 local max. So all the turning points once again represent your local mins and maxes there. These are local mins because they go from decreasing to increasing. They change direction that way. Increasing to decreasing local max, decreasing to increasing local min. Okay, we're almost at the half-hour mark. Like I said, I couldn't promise you how long this would be. That's 6 problems down, and I have 12 more to go. The good news is you're hearing a lot of the stuff that will make sense for the rest of the way. You almost don't need to hear any more things. Almost. Let's look at number 7 now. On number 7, let's refer to what kind of graph this will become if you expanded this. We have an x times an x squared. That'll leave you with an x cubed, but not just any x cubed, a negative x cubed. And a negative x cubed graph has the basic nature of start up, finish down. Start up, finish down. We know that because it's negative, it'll have that reflection piece. It won't go this way, it'll go this way. So we know when we graph this, for end behavior wise, we start from the left and up, and we finish right and down. That's something to note. Now, that's what we know. It's an x cubed graph, odd degree. That's what it's going to do. Let's find our intercepts. Remember, the intercepts go zero product property. If negative x equals 0, then x equals 0. That is one of your intercepts. And then if x minus 2 equals 0, then x equals 2. That's the other one. This is, however, squared here. That means this one has a multiplicity. This has a multiplicity of 2. A multiplicity of 2, which means when we hit the x-intercept of 2, it's going to bounce off of that one right there. I can make this one a little taller for you guys. It's not going to matter too much there. But there is an x-intercept of 0 and an x-intercept of 2. And of course, at 2, once again, there will be a bounce back. A bounce off. Bounce back, bounce off. I don't know how to say it. Now, once again, how could a cubic possibly hit these 2 points and be a cubic? It doesn't do this. It will bounce off. So I'm going to start from the top here on the left side. I'm going to hit through 0. I'm going to hit a turning point, a local min. I'm going to bounce off of x equals 2 right here tangentially, and I'm going to finish downward. That's how a negative odd degree function would behave. That's what this one's doing right there. There's the graph. You can see how much faster that one went. How many turning points are there? There are 2. 1, 2 turning points. There is no global max or min because it goes up and down forever. Odd functions will not have a global max or min. Odd degree functions, I should say. There's no global max or min. And then as far as local maxes and mins here, we do have a local minimum right here because that's a turning point from decreasing to increasing. And then we have one local max right here where it bounced off at x-intercept of 2 right there. Awesome. So you can see how fast that one went. And then finally, number 8 here, let's get to the intercepts and the basic nature of the graph. We have the opposite of an x times an x cubed. X times x cubed is x to the 4th, but when we multiply by a negative, that'll be negative x to the 4th. That means an even degree function that's negative will start down, finish down like this. There might be turning points in between, but it will start down, finish down. That's what even degree functions do. Now, which intercepts will it hit? It'll hit an x-intercept here of 1. I should really be labeling this as x-intercept. It'll have an x-intercept of 1, and it'll have an x-intercept of negative 2. Once again, it's like the opposites, right? But this one has a multiplicity of 3. That's kind of interesting, in a multiplicity of 3. We'll see what that means in just a moment here, because you could misconstrue this graph. You wouldn't be completely wrong if you do what I'm about to do here, but if you saw it on a graphing calculator, you'd see why we want to do something different here. So right here, I'm going to hit negative 2 and 1 as my intercept. So let's kind of put those in. I'm going to get negative 2 right here. I'm going to get 1 right here. And then let's use different colors. Use like a red. So negative 2 and 1. And you know, if we start down, finish down, I guess you could conceivably say that, okay, the graph is going to go up here and it's going to go down here. And that's fine, right? Because an even degree, and that's what we want. But a multiplicity of 2 had some sort of meaning behind it, and that was a bounce back. And I'm not saying this thing bounces back, but it bounced back because it behaved like a quadratic behaves, vertex-like. It has that curve through and bounce back. This thing has a multiplicity of 3. Cubic functions and odd degree functions have this innate behavior to them of curving through curving through its center point in such a way that it kind of sharpen, it has that accentuation and that sharpen thing. It doesn't go straight through like a linear does, right? Like linears have that behavior going straight through. In fact, that's why these do go straight through right here, because that's a multiplicity of 1. It behaves very linearly in those ones. But a cubic, when it has a multiplicity of 3 at, this is at -2, The cubic, even though I start from the bottom and go through it, it's going to behave like a cubic here. It's going to curve through it like that. And then this one is a multiplicity of 1, so this one's going to go through very linearly like that. So the graph is going to go more like this. And again, you can see it on a graphing calculator. Mine's obviously not as tall or whatever as it is. I'm only fitting on the paper, and that's what you're going to have to be able to do. But you want to give it this cubic-like nature right here of curving through right there. I could do even better with you there. I'm going to do it one more time and just get it a little bit sharper. Cubic does have a little more of a sharper edge to it. Kind of like that. That's still not perfect. But anyway, so there we go. There's your quartic function with a multiplicity of 3 at -2 on x. So you've seen pretty much the extent of everything that you need to know that's unique and different about these graphs. I don't think I have many more ways to trick you on this thing. Okay, turning points. Now you might think that this is a turning point right here. It's not. This thing is plateauing right there. It goes from increasing to constant to increasing. A turning point is a point where it actually changes direction from increasing to decreasing. This is not one of them. At least that is my belief, because the turning points are the maxes and mins of this thing. So there's only one turning point right there. There's a turning point, or there's one turning point there. Because it's a quartic function, it does happen to have it one absolute extreme. In this case, it's an absolute maximum because it's the highest that it goes. So it has an absolute, or global, I should say. It does have a global maximum. I'm going to pause this in a second, double check on the turning point here, because you know what? It might be something to reference. But this turning point is not a local max or min. That's the important point that I want to state. There's only one local max or min. Right here, there is a local max. There is no local min. This is not considered either or because it just plateaus right there. Let me check really quickly. I do have a teacher guide. I'm going to pause this thing. I have a teacher guide, and I'm going to see if they consider this one over here a turning point. But again, if it is, it's not a local max or min. One sec. Okay, before I find it, I'm going to go ahead and state that I believe it's not. The reason why is because their idea of turning points is really just making sure that you understand the local max and mins for these functions. Anyway, that's just what I want to say. Hold on. Okay, I am back, and they just state one turning point. Yes, so this plateau, turning points need to change direction. Excuse me. They want to mention the turning points to note that how do I get back to this intercept? I need to change direction. Right, this one's going through an intercept there. It's kind of a different thing. Okay, so those are numbers 5 through 8 right there, and that's, you could use in graphing calculator, but there's me describing that, and that'll make the other ones a lot faster now that you've seen those. You know what to do. Let's breeze through the rest of these so it doesn't have to be explained what's happening on those. Here we go. So sketch the graph of the polynomial function. These books, man, they do these a lot. Sketch the graph of the polynomial function. Okay, we've done this so much, and we don't have to explain anything else beyond it, but let's find the intercepts. So there's an x-intercept here. So see, these are going to go a lot faster now, guys. X-intercept of 0, because if x squared is 0, then x is 0. But this has a multiplicity of 2. And you know what? Eventually, maybe after this problem, maybe I'm not going to write this stuff out. I want you to just kind of understand as I'm doing it with you what it is that I'm doing. This is x equals 2. That's an x-intercept of 2 right there. So we know it's going to hit here. With a bounce back, we know it's going to get hit here. This is x squared times x. That makes it a positive cubic function, which means it's going to start down, finish up. Cubics, odd degree, start down, finish up, positives. So, and it has a multiplicity of 2 at x equals 0. So that means it's going to bounce back at 0, and then it's going to hit a turning point, a local min, if you will, and it'll finish upward there. And that is our graph. That is our graph, and that's it. Number 10. Let's plot the intercepts. X plus 1 means x is -1 is an intercept. X minus 2 means x equals 2 is an x-intercept. And x minus 3 means x equals 3 is an x-intercept. Again, kind of just changing the sign. If x minus 3 equals 0, x equals 3, things like that. Negative x times x times x. This is a negative cubic, an odd degree. That's negative means it's going to start up, finish down. And all these are multiplicities of 1, so they'll go straight through in that linear-like fashion there. So it's going to go like that right there. Let's go ahead and draw that one. Starting from the top, bounce. I don't want to say bounce back. Turning point. I want to say bounce back. Ugh, I don't want that last point. I want to save the bounce back name for when I'm hitting an intercept and bounce back. But turning point, local max, local min, etc. Ugh, it's hard to kind of draw that with my tablet thing that I have. But anyway, so there's the graph. That's the appearance. Basic nature. That's all we're trying to find. That's all we're trying to find. All right. Last one on this page, number 11. I don't know what goes beyond this, to be honest. I think I'm skipping 2 problems, 12 and 13. So after this, you'll see, I think, number 14. 12 and 13 are different ilks of problems. I'm going to focus on these. All right, x-intercepts. X equals 0 is one of them. By the way, if you want to write this in a factored form that looks like the others, if I expand this thing out, I could write this as x minus 0 times x plus 2 times x plus 2 times x minus 1, if that makes sense. X is x minus 0. So you can see if x minus 0, x is 0. Take the opposite of 0. X plus 2 appears twice. That's that multiplicity of 2 thing, and x minus 1. So it is a quartic. X times x times x times x is x to the 4th, or x times x squared times x. So anyway, x equals 0. X equals negative 2. You got to note the multiplicity. There's a multiplicity of 2 here because it's squared. And then x equals positive 1 right here. This is a positive quartic. Positive quartic, which means start up, finish up. That's what even degrees will do. The multiplicity of 2 occurs at x equals negative 2, so it's going to bounce back here at negative 2. It's going to hit a turning point here, go through 0. Hit a turning point here, go through 1. See how much faster these go after you don't just rely on the graphing calculator for these things and you answer these the way you're supposed to. And there it is. There it is. That's awesome. All right, so let's skip at 12 and 13 and go to 14. Now we're going to write functions based on what we see here. Let's kind of do the backwards approach of what we did from the previous ones, and we're doing it for 14 through 17 at the very least. Let's check these out. Write a cubic function, so we know it's going to end up as an x cubed. They say intercept form, so leave them as factors. That means we're going to have 3 factors. 3 factors. They might be squared or cubed, all depending on if there's a bounce back or nature of it. For the given graph, whose x-intercepts are integers, assume the constant factor a is either 1 or negative 1. When they're talking about a, guys, they mean in factored form. It's like, you know, like this. A is like that stretch factor right here. They're just saying, we're not going to turn it into a 2 or a 3 or whatever. Otherwise, it's an open-ended answer. We'll either make it positive or negative based on whatever there is. And we're going to write our factors in here based on our intercepts. So let's investigate a little bit, guys. Based on this graph here, we have the following x-intercepts. We get an x-intercept of negative 3. We have an x-intercept of negative 1. And we have an x-intercept of positive 1. Those are our x-intercepts. Now, if we go backwards from what we saw before, as far as where these come from the idea of zero product property. Either, if I add 3 to both sides, either x plus 3 would have equaled 0, add 1 to both sides, x plus 1 equals 0, or subtract 1 from both sides, x minus 1 equals 0. And in factored form, that comes from multiplying all these 3 together in the nature of a zero product property, where all these equals 0. But of course, that's for x-intercepts. What about when you multiply these for the whole graph? Just make it an f of x. So f of x equals x plus 3 times x plus 1 times x minus 1. Now, these are the 3 intercepts for this y. And as being a cubic, let's confirm it's a cubic. This is x times x times x. It's x cubed. And as an odd degree function, as a positive odd degree function, it should start down and finish up. And that's what it does. Starts from the bottom, finishes at the top. So this is the factored form polynomial, or intercept form polynomial, of this function right here, assuming this was in front was a positive 1 right there, which it was. That's what they told us to do. And that is our answer. So here's what we're going to do for the others, because I'm not going to write all this stuff in between right here. I'll write these numbers right here, but then the rest I'm going to switch the sign. You find the intercepts. You find the intercepts. You determine their multiplicity. These are multiplicities of 1 because they just cross through, cross through, cross through. They told us it's a cubic. So 3 intercepts right there in this cubic. We write their opposite for factored form, right? If x plus 3 equals 0, x is negative 3. So write their opposite here in a function like this. And we might have to reverse direction and change sign and make it negative. The negative version of this, like this, would have gone like this right here. It would have just flipped over if it was negative, but it is not. Next one looks like it is, though, so let's investigate number 15. I do like these questions, actually, quite a bit. I applaud the book for that. X equals -2 is one of our intercepts, and it has a multiplicity of 2. This will be important when it comes to writing out its factored form. Because, oh, how do I know it's a multiplicity of 2? Bounce back. Bounce back. Now, you might ask, how do we know it's not a multiplicity of 4? A multiplicity of 4 will bounce back. Well, because this needs to be a cubic function. So I can only have at most 3 factors. And I have 2 of the factors right here, and I have 1 factor right here at x equals 3. So our factors, guys, our factors are x plus 2, right, the opposite of the -2, and x, minus 3. X plus 2 and x minus 3. Now you might say, wait a minute, x times x is just x squared. This is a quadratic. You're right, it is a quadratic. We need to turn this multiplicity of 2, we need to give this a squared right here. So now it's x squared times x, that makes it x cubed. So you're done, right? This is a cubic. It has a multiplicity of 2 right here and a multiplicity of 1 right there, and we're done, right? Hold on a second. This is an odd degree that started from the top and finished downward with an end behavior of positive x, negative y. This must be a negative cubic function right there. There's that -1 that they're talking about. Assume a is positive. I think I scratched myself. Assume a is positive or -1. A is -1 this time, and this is a negative that goes in front that makes this thing go upside down, if you will, that makes it flip over. Okay, so there's that one. So you're kind of seeing the nature of how these things come to be, and we create it, and you can double check on a graphing calculator, but there it is. All right, 2 more 60. Well, we have 2 more beyond this here. Oh, maybe 3 more, I forget. Hopefully I can finish within the hour. Write a quartic function in intercept form for the given graph whose x-intercepts are integers. Assume the constant factor. Okay, so everything's the same. Just write a function. They tell you it's a quartic this time. My mind was going blank when I was just reading. But here we go. Now, for a quartic function, start up, finish up kind of thing, because even degree, right? That's what's going to happen. Let's pull out the intercepts here. We get an x-intercept of -3, an x-intercept of 0, good, they give us a 0, 1, an x-intercept of 2, and an x-intercept of 4, all which go through very nice and naturally like a linear thing, so they're multiplicities of 1. There are 4 of them. These are our only 4 factors when it comes to writing them in our factored form right there. So we know that this, take the opposites of these values, right? X plus 3 here, and, x minus 0, I mean, that's, we're not going to officially write that. I'm going to change this in a bit. This is x minus 2 and x minus 4. If you recall, as you saw in the previous ones, guys, x minus 0 is just x. And, whenever you see an x, we tend to write it just out in front. It's just cleaner to have one of these here multiplied by all of the other binomial quantities right here, like this. I used to be a big fan of kind of putting these in a certain order in the past, like numerical order increasing or something like that. Now, should this be a positive 1 or negative 1? Well, this is start up, finish up. That is a positive even degree behavior. So just positive, don't change the sign. That is the factored form of this one. Okay? And last one for, well, I don't know what happens after this. I keep saying last one. Last one on this page on number 17 here. Let's investigate. I got an x-intercept here of -2. That one has a multiplicity of 2. All right, multiplicity of 2 there. And x equals 3 also has a multiplicity of 2. Again, it is the nature of the graph to have that bounce back multiplicity thing that's going on right there, as it doesn't go through, but it touches tangentially. So we know as a quartic here, it should only have 4 intercepts at most. It kind of has 2 intercepts here and 2 intercepts here with the multiplicities. So our thing here is x plus 2 squared, right? Opposite of -2. X plus 2 squared, that's the multiplicity of 2, times x minus 3 squared right there, again, multiplicity of 2. That's x squared times x squared, which gives us x to the 4th. Not done, though, because this one has a nature of start down, finish down. That's what would be true of a negative quartic function. So we got to put the negative symbol there, and we got to box our answer, and there it is. You guys are doing tremendously here. More power to you. So those are those ones right there. We are almost done now. I should finish within the hour, all depending on what questions. Oh my goodness. I forgot this was one of the questions. All right, number 18. Let's see what this one's all about. Let's see if we can answer all these now that we've understood. I don't really know what this... I knew that it looked fun, so let's do it. Select all statements that apply to the graph of f of x equals x minus 1 quantity squared times x plus 2. When select, I assume means I can just circle them. So if I circle them, that means it's correct. So let's check them out. The x-intercepts are x equals 1 and x equals negative 2. Yes, x equals 1 and x equals negative 2. If you recall, it's the opposite thing because x minus 1 equals 0, therefore x equals 1. X plus 2 equals 0, therefore x equals negative 2. That is true. This one has a multiplicity of 2 at the negative 2, 1, but those are the x-intercepts. Those are the only ones. That's the only place it's going to touch the x-axis. Negative 1 and positive 2? No. I'll go and cross those out if they don't work. So that's the opposite one, right? It's not that. And it looks like, at least when I look at these, it looks like they're flip-flopping everything that they're kind of referring to. You know what I mean? It's that they're saying one or the other now that I look at it. The graph crosses the x-axis at x equals 1. You know what? Let's graph this first because that can help answer some of the things here. So x equals 1, x equals negative 2. When x equals 1, guys, it does have a multiplicity of 2, so it will bounce back here. X equals negative 2, it just crosses through. This is x squared times x. It's a positive cubic, so it's going to start down, finish up. It's going to come through here. Oh my goodness. Which one is the multiplicity of 2? The 1. So it's going to start down, finish up. It's going to cross through this one, turn around, and hit this one, bounce back, and finish up. Okay, so we know the nature of it. Let's try and answer the rest. The graph crosses the x-axis at x equals 1 and is tangent. This is for bounce back. Tangent is touching just at the 1 point, grazing it, and going back. Tangent to the x-axis at x equals negative 2. It's not that one. I think it's the opposite. So this one here, the graph crosses the x-axis at x equals negative 1. Boom. And is tangent to the x-axis at x equals 2. It bounces back there. Yes. It's that one there. So there's our bounce back. Let me actually put the bounce right there because that's the one we're actually going to talk about. Okay, the graph is tangent to the x-axis at x equals 1. Wait a minute. Are these the same thing? Oh, are they going to... Oh, that's... Why do they even bother? The graph is tangent to the x-axis at x equals 1 and crosses the x-axis at x equals 1. Yes, that's the same thing as D, only they reverse the statement. Unless there's something I'm not seeing here, that's the exact same. They didn't say y-axis or anything, did they? No. Okay, so that's... This is dumb. All right, so yes, E, and likely no to F, because I think... This is... No, I'm dumb. Hold on. D is wrong. I did not read this. That says negative 1 and positive 2. I shouldn't discredit the book as much. Okay, D is incorrect because those are not our intercepts. Negative 1 and 2 are not our intercepts. They are 1 and negative 2. Okay, good thing I read that a little better. So, okay, C, D, E, and F are all among the same things, only you should really ignore D and F because those were not our intercepts to begin with. C and E had our intercepts of 1 and negative 2, which is what they were, right? But it's not this one, and it's this one on E, so ignore the others there. I apologize for that. My bad. Okay. There is a local but not global minimum, or a local but not global minimum occurs on the interval between negative 2 and 1, and a local but not global maximum occurs at x equals 1. Okay, let's go to some more of the features here. Let's look. So there's a turning point right here. This is a local max. There's a turning point right here. That's a local min. Okay, so we have a local max. We have a local min. Great. Now, what about the local max and local min? Well, this local max occurs between x equals negative 2 and x equals positive 1. So there's a turning point. So this is local, not global. So just ignore the not global just because it's going to be a little weird to say. There's a local max between negative 2 and 1 on x. Excuse me. Yes, between negative 2 and 1 on x. There's a local min at x equals 1. Not between something. Well, depending on what they give us. But there's a local max between negative 2 and 1. There's a local min on x equals 1. So let's find the one that says local max between negative 2 and 1. A local min between negative 2 and 1? No. Automatically, that's a no. A local max between negative 2 and 1? Yes. Let's see what else they say. And a local min at x equals 1? Yes. So at x equals 1, there's a local min. Between negative 2 and 1, there is a local max. That one's good. These might be no, depending on what we're saying. Local min between negative 1 and 2. No, see, now they're saying between negative 1 and 2. They're kind of doing no. So these are between negative 1 and 2. That's not even our intercept things that we're worrying about. So our final answers, ones that are true on this, are A, E, and H right there. A, E, and H are the correct things. They're just letting you kind of filter and play through that. Okay, awesome. That wasn't too bad of a problem. All right, number 19 here. Let's see if we can get in within the hour. Explain the error. Ooh, I love these. Error analysis. A student was asked, hold on. Okay, a student was asked to sketch the graph of the function f of x equals x squared times x minus 3. Describe what the student did wrong, then sketch the correct graph. Sometimes people would sketch the correct graph and figure out, well, here's what you did, you idiot. Okay. X squared times x is x cubed. It's a positive x cubed, so they properly started down and finished up. No problem with that. They have their intercepts of x equals 0 right here and x equals 3. No problem with that. It appears that the issue is that at x equals 0, there should be a multiplicity of 2, which means there should be a bounce back there. Here is where they should have their bounce back like that, and then it should curve through. So I'm kind of graphing it before I do. And then this one here is where they did the bounce back. That should just be normal, behaving very linearly right there. So their issue, and I say bounce back where this thing would say hits tangentially or whatever. So at x equals 0, there should be a bounce back. I'm going to say it the way I say it. There should be a bounce back, and it should cross through x equals 3. They have this reversed. They have this idea reversed, right? Because of the nature of the quadratic, because of the multiplicity there. So with a multiplicity of 2 here at 0, it should bounce back in 3. The rest is fine. I mean, that it makes your graph way different. But the end behavior is correct. The intercepts are correct. It's where they decided to bounce back that's the problem. So it should bounce back at 0, touch tangentially, and then should cross through x equals 3. And again, there's no knowing specifically where that local minimum is. Maybe it's a lot lower, whatever. But that is where that one occurs there. All right, that's number 19. I believe there might be a number 20. Let's see. One more that I'm going to do number 20. I'm going to skip number 21 here. Make a prediction. Oh, no, I think we can do this. Knowing the characteristics of the graphs of cubic and quartic functions in intercept form, sketch the graph of the quintic function. Quintic function means degree 5. This is x to the 5th power. There's no prediction on this thing. We know what's going on. I'm like, come on, guys. We have x equals 0 as an intercept with a multiplicity of 2. If you stuck through this, congrats. You guys are doing great. Hopefully it's making sense. An x-intercept of negative 2 and an x-intercept of positive 2 with a multiplicity of 2. So we cross here. Well, we touch here, here, and here. At 0, there's a multiplicity of 2. At 2, there's a multiplicity of 2. Because it's a quintic function, it's an odd degree, and it's positive, it's going to start down, finish up. So we know it's going to start down, finish up. It's going to cross through negative 2 naturally. It's going to cross through negative 2 naturally from the bottom. It's going to approach a local maximum, a turning point here. It's going to bounce back at 0. It's going to hit some other, I don't know how high or low it goes, but it's going to hit some other local maximum here. It's going to bounce back at 2 and finish up. Once again, we do not know specifically where these points are. You can either use a graphing calculator and let it do it, or I can show you some calculus and figure those out specifically for you, which I plan or care to do. It takes quite a while to do. But, you know, it might go high up like this and a little lower like that. I don't know for sure. They might be the exact same even height. But those are the bounce back. It is a quintic odd degree. That's the nature of where it does all the bounce back stuff. Okay, guys, that ought to do it for this one right here. I sure hope it started to make sense what we were talking about with the end behavior, degrees, factored form, intercepts, multiplicities, and bounce backs. All this stuff went into a single section, and really there's no way to break it up into different sections. This is the section. And thanks for sticking through the hour, guys. I sure hope a lot of this made sense. This is Mr. Robinson. Thank you so much for watching, and I will see you in the next one. Take care.